In 1998, the Mars Global Surveyor pointed a laser at the red planet and began measuring the reflection time of light pulses. By tracking those returns, the Mars Orbiter Laser Altimeter mapped the entire planet pole to pole, establishing altitudes precise enough to reveal ancient Martian streams and valleys. When we look at standard two-dimensional maps, we are looking at visual illusions of depth. They are flat representations shaded to mimic shadows. True computational spatial analysis requires a different architecture, the Digital Elevation Model, or DEM. To understand how this works, we have to construct a DEM from first principles, translating physical reality into a discrete, computable grid. Building and correcting these models allows for the mathematical simulation of the Earth's physical phenomena. At its structural core, a digital elevation model is a continuous raster data set. A pixel grid is divided into data cells, and every cell is anchored to an exact horizontal coordinate, the x-axis for longitude and the y-axis for latitude. Crucially, a DEM adds a vertical z-axis value for elevation. To ensure global consistency, this z value is mathematically normalized against mean sea level. Linking the x, y, and z coordinates permanently transforms the chaotic physical topography into a highly ordered, computable environment. The utility of this computable environment is strictly governed by the density and accuracy of its underlying grid. There are three core resolutions. First, spatial resolution, which is the physical distance between sample points, like moving from a 30-meter to a 1-meter grid. Second, vertical resolution, which is the height accuracy compared to true ground level. And third, temporal resolution, which tracks data recency and is critical for monitoring ongoing changes. To measure this accuracy, modelers calculate the root mean square error, or RMSE, comparing the modeled elevation against ground truth reference points. Practitioners must constantly balance these three metrics based on the scale of the project and the processing power available to them. High-resolution data sets require specialized remote sensing methodologies to capture data at scale. When a remote sensor scans the Earth, the raw signal always bounces off the first physical object it hits. This captures a chaotic mix of tree canopies, rooftops, and the actual ground. To penetrate that cover, active sensors like LIDAR fire laser pulses from aircraft, recording multiple returns as the light passes through gaps in the foliage. Alternatively, SAR interferometry, or InSAR, uses satellite-based synthetic aperture radar, collecting multiple angles to build a three-dimensional representation. The collected point cloud is filtered into distinct layers. The top layer, the Digital Surface Model, DSM, isolates the canopy and built environment. The bottom layer, the Digital Terrain Model, DTM, strips away physical obstructions to reveal the bare topography underneath. Isolating this bare Earth DTM is an absolute prerequisite if you want to analyze natural water flow or foundational geomorphology. However, even after isolating the bare Earth, the raw mathematical raster data remains noisy and often contains critical vertical errors. An elevation profile can contain various anomalies. First are peaks, the sharp upward spikes which are artificial artifacts generated by sensor anomalies. Second, and more problematic, are sinks, which are deep downward drops. These are artificial pits surrounded by higher elevation. Sinks frequently occur in highly flat areas when algorithms attempt to store continuous decimal elevation data as simple rounded integers. Before analysis can begin, algorithms must identify and fill these sinks to create a continuous surface. Achieving a depressionless elevation model is mandatory. Without it, predictive fluid models will trap simulated water in artificial digital pits. A fully corrected DEM functions as a dynamic analytical engine, allowing us to compute advanced physical derivatives from the grid. This includes slope, the foundational derivative calculated by comparing z values of adjacent pixels. By defining terrain steepness, we predict mass movement and landslide risks. Next is aspect, which calculates the compass orientation of those slopes. Because aspect dictates a region's exposure to solar radiation, it directly drives localized weathering patterns and vegetation growth. Combining these spatial derivatives allows us to execute complex physics equations, like the topographic wetness index, which calculates the natural logarithm of the upslope contributing area over the tangent of the local slope. Calculating these derivatives translates raw spatial geometry into highly accurate localized simulations. These simulations are applied directly to human environments. Topographers model urban flood extents to prepare for catastrophic weather events, while civil engineering utilizes these models to route rail networks and power lines safely through optimal mountain gradients. Scaling up, NASA glaciologists analyzing Arctic DEM data revealed a massive 22-mile-wide meteorite impact crater hidden beneath more than a mile of solid ice in Greenland. Digitizing depth provides the quantitative foundation needed to analyze the mechanics of the Earth. The digital elevation model stands as the ultimate spatial ground truth, translating physical chaos into actionable digital intelligence.